Alright, you made it to part 2. Use the definition of continuity and the properties of limit to show that the function is continuous at the given number a. So first, we have to show that the function is defined when x is equals to -1. So a, we have f of x equals to parenthesis x plus 2 times x to the third raised to the fourth power at x equals to -1. We have -1 plus 2 times -1 to the third and then raised to the fourth. So that is equals to -1 minus 2. That is -3 raised to the 4. 9 times 9 is equals to 81. So f of -1 is defined. This -181 is a solid point. And then we check the limit, right? So the limit, I know you have to check the left and right, but do you really need to? The answer is no. Because there is no square root, I don't see any discontinuity because this is just a polynomial. So for the limit, you can just plug in x equals to -1. You have x plus 2x to the third, the entire quantity raised to the fourth power. So once you plug in -1, you have -1 plus 2 times -1 raised to the third to the fourth, so that is equals to 81. And then these two are equal. So we just show that the limit as x approaches to -1 of f of x is equals to f of -1. So that means in f of -1, we have a solid point at -1 comma 81. And then the left limit is approaching to that point. The right limit is approaching to that point. So we have a left limit and the right limit. They both stop at that point and pass through that point. That means the function is continuous when x is equal to -1. I am not saying that this curve is the curve of the function. I am just give you an example. We don't need to know the exact curve. So based on these three conditions, this is what I can sketch. All right. So B, we have f of x equals to 2 times the square root of 3x squared plus 1 at x equals to 1. Alright, so let's check f of 1. So that is 2 times the square root of 3 times 1 squared plus 1. So we have 4, right? So 2 times root 4. So 2 times 2 is equal to 4. So that tells me that 1 comma 4 is a solid point. And then next, we have to check the limit as x approaches to 1. X approaches to 1, you plug in, there is not going to be a problem, so you can just plug in. So 2 times the square root of 3x squared plus 1, it's safe to plug in. So that is just, you don't need the limit anymore because you already plug in. 3 times 1 squared plus 1, so that is 2 times root 4 is equal to 4. So we just prove that the limit as x approaches to 1 of the given function is equal to f of 1. F of 1, so that is number 2, that is number 3, that is number 4. That means we are saying that at x equals to 1, there is a solid point at 1 comma 4. And then the left limit is approaching to that point, the right limit is approaching to that point, and it is safe to just pass through at this point. So we have a solid point, left row and right row, they are connecting to that point, and we can drive through that point. So that means the function is continuous when x is equal to 1. So that is how you show the three conditions. Okay, so moving on to the next type of problem, we have some piecewise function. Explain why the function is discontinuous. Okay, so tell me why. So A, we have a piecewise function. So let's start with writing down the problem. So A, we have f of x equals to it's a piecewise 3x minus 5, 2. This is if x is not equal to 1. This is if x is equal to 1. Okay, so that tells me f of 2, I can evaluate that, no, not f of 2. This is a mistake. This is equal to 1. So when x is equal to 1, we have 2. So that means 1 comma 2 is a solid point. And then x not equal to 1, right? So we cannot have x equals to 1 exactly for the 3x minus 5. So therefore, we have to check the left limit and the right limit. So this is a limit as x approaches to 1. So we have 3x minus 5. Speaking of the left-right limit, it is safe to plug in a 1. The answer is yes, it is safe to plug in. So you don't really need to check the left limit. So we have 3 times 1 minus 5, that is equal to negative 2. Looks like as x approaches to 1 from either side, we have a negative 2. So this is an open circle. So can we get the graph really quick? Yep. So when x is equals to 1, we have a point at 1, 2. So this is a solid point. And then when x approaches to 1 from either side, we have negative 2. So negative 2 is like right here. It's an open circle. Since 3x plus 5 is a straight line with an increasing slope, so the line will just look like this. Look at the graph. Is the function continuous at x equals to 1? The answer is no. Although the left limit and the right limit, they are approaching to the same point, that point is not a solid circle. So the solid circle is jump up here. So when you drive, let's say at this point, you can pass through the entire curve because at x equals to 1, there is an open circle. So you have to pick up your pencil. When you sketch the entire curve, you cannot sketch the entire curve in one draw. You have to pick up your pencil to finish the remaining pieces. This one, so the limit and the solid point, they don't join at the same place. You can say the limit as x approaches to 1 of that function is not equal to f of 1. So that tells me the function is discontinuous at x equals to 1. All right, so let's move on to P. So B, the graph might be a little bit difficult to sketch if you don't have a calculator. So let me switch color for the next problem. Let's use red. So part B, I will copy the problem for you, so you don't need to go back up. So this is x squared plus 2x, and then x to the third minus 6x. So this is if x is less than or equal to negative 2. This is if x is greater than negative 2. All right, so we are checking out a equals to negative 2. So let's check out the solid point. So f of negative 2. Can you tell me which piece I have to pick? Where do you have to look right now? You have to look at the inequality. Where is the equal sign? The equal sign is up here. So we have to pick the first piece, the parabola, the second degree. So that is negative 2 squared plus 2 times negative 2. So we have a 4 minus 4 equals to 0. So that means when x is equals to negative 2, we have a 0. This is a solid point. When x is equals to negative 2, we have a 0. And then we check the limit. So the limit as x approaches to negative 2 from either side, x to the third minus 6x. How come I don't separate them into two limits? Should I? The answer is yes or no. This one is greater than. Should I? Think about it. The answer is yes, I should. Because why? Because as x approaches to 2 from the right side, x approaches to 2, number line, this is a negative 2, sorry. This is a right side, right? This is a left side. So this is x approaches to negative 2 from the right. This is x approaches to negative 2 from the left. As x approaches to negative 2 from the right, we are looking at a number that is greater than negative 2. So that means we are looking at the third power. So the third power is, I just wrote the third power. So that is negative 2 raised to the third minus 6 times negative 2. So that is negative 8 plus 12. 12 minus 8 is equal to 4. That is my right limit. And then the limit as x approaches to negative 2 from the left. Am I going to pick the same piece? No. X approaches to 2 from the left is something less than negative 2. So you should pick the second degree. So this is x squared plus 2x. That is a negative 2 squared plus 2 times negative 2. So we have 4 minus 4 equals to 0. Are they equal? The answer is no, they are not equal. What is not equal mean? The left limit and the right limit are not the same. That means limit as x approaches to negative 2 from either side of the function is undefined, or you write DNE, does not exist. Now, we have a condition. This is a solid point, but the limit doesn't exist. So number 3, we have to write the limit as x approaches to negative 2 from either side of the piecewise function is not equal to f of negative 2. The limit doesn't exist. It equals to nothing. But when x is equals to negative 2, you have a 0 exactly. So they are not the same at all. So therefore, the function is not continuous, or you can say the function is discontinuous at x equals to negative 2. What is the limit look like? Not the limit, the graph. We can take a quick guess. So this is my negative 2. As x approaches to 2 from the right, we have a 4. So this is a 4. We have something right here. As x approaches to 2 from the left, we have a 0. So the 0, negative to 0, is a solid point. So as x approaches to 2 from the left, we have this. As x approaches to 4 from the right, since this is already a solid point, there is no way to put the solid point right there. Because if you do, then it is not a function, because the vertical line test is not passed. So as x approaches to 4, you have something like this. So there is a discontinuity. You can call this a jump discontinuity. Why? You sketch the graph. All right, so you are driving, right? So starting right here, you drive to negative 2, and then the road is disconnected at negative 2, and then you jump. So it looks like if you hold on the line for too long, they will just assume that you want a straight line. So driving and then stop at negative 2, and then you jump. So that means you have to pick up your pencil to finish the rest. So I just pick up my pencil, so the graph is not continuous or discontinuous at x equals to negative 2. So that is how you explain it. Let's do part C. So I'm going to switch color for part C. Let's do blue. So in part C, we have f of x. Oh, it's a highlighter. Blue. So this is back to yellow. Let's erase that. So we have f of x. This is a part C equals to 3 pieces. So we have x minus 6 divided by x minus 3, a 2, and a square root of 4 plus x squared. This is x less than 0. This is x equals to 0. This is x greater than 0. So right off the bat, we have a solid point right here when x equals to 0 exactly. So we have f of 0 is equals to 2. So 0 comma 2 is a solid point. And then this one is left side of 0. This is the right side of 0. So I want to see if the left limit equals to the right limit. And then you check the limit as x approaches to 0 from the left. Which piece should I pick? Good question. Number line, 0. So this is a 0 from the left. This point is a 0 from the right. This is your left hand. And then this is your right hand. As x approaches to 0 from the left, that means x less than 0. This is x greater than 0. We pick the first piece. X minus 6 divided by x minus 3. I don't see a problem with plugging in a 0. Minus 6, 0 minus 3. You have a 2. And then limit as x approaches to 0 from the right. You pick the other piece. Is 4 plus x squared. No question in plug-in. 4 plus 0 squared. So you have that equals to 4. Are they equal? The answer is they are not equal. Not equal means the limit is already Actually, why do I do this? Is equals to 2. Forgot to look at the square root. They are equal. Okay, that changes everything, right? So they are equal. So that means limit as x approaches to 0 from either side of the function is equals to 2. And this is exactly equals to f of 0. So the limit is equals to the solid point. So therefore, the function is continuous. All right, is continuous at x equals to 0. So at this point, we can sketch a graph when x is equals to 0, y is equal to 2. So there is a solid point. The left limit and the right limit, they are approaching to that solid point, and they are connecting the solid point, and we can sketch the entire curve. Look at my highlighter. We can sketch the entire curve without picking up my pencil. So that means the function is continuous when a is equal to 0. All right, so far so good. Let's do the last one, and then we move on to another theorem. So the last one is a removable discontinuity. So removable discontinuity, what is removable discontinuity? At the beginning, once you plug in a number to the function, the entire function is failed. So most likely, you have a 0 in the denominator. But you can do algebra to remove the 0. So if that is successful, then the 0 you remove is a removable discontinuity. So this is a perfect example. First, let's factor the function. The factor, you don't need me to go over how to factor, right? So f of x, that is equal to, so that is x plus 4 times x minus 3 divided by x plus 2 times x plus 4. So that is how we factor. And then can we simplify anything? Yep, we can get rid of the x plus 4. So the function is equal to x minus 3 divided by x plus 2. All right, that is how you simplify. But before you simplify, look at the factor form. Look at the denominator, what x cannot be. So if you look at this denominator, this piece, we can say that x cannot be equal to -2 and -4. If x equals to either of this, then you have a 0 in the denominator, makes the function undefined. So let's say we draw the domain. So we have a number line. We punch a hole at -2, punch a hole at -4. So x cannot be equal to these two numbers, but x can be equal to everything else. So what is the domain? The domain is from -infinity to -2, from -2 to -4, from -4 to infinity, positive infinity. These are intervals. That is the domain. You did that. You learned this back in pre-calculus or intermediate algebra, right? But in calculus, we are going to take one more action. Which one we just cancel? We just cancel x plus 4. So that tells me x plus 4, we just cancel x plus 4, right? So that tells me x equals to -4 is a removable discontinuity. Because you cancel the x plus 4. How come I don't say x equals to +4? Because the x plus 4, when you plug in a -4, that creates a 0 in the denominator. So we call that a removable discontinuity. What about x equals to -2? It's a non-removable discontinuity. What else can we say? If you remove this, then this is an open circle when you do graphs. What about x equals to -2? You are unable to move that, then this is a vertical asymptote. In the future, I will just call this a V8, vertical asymptote. So that's how you do removable discontinuity. Cool, right? So there is one more theorem to go over. I will see you all in the next video.